You can build a vault door with 10 trillion combinations, but if the hinges are exposed, the lock doesn't matter. In digital security, mathematical complexity evaporates the moment an attacker finds a structural shortcut. This concept is formalized in Kirchhoff's principle. It states that a cryptographic system must remain perfectly secure, even if the attacker knows exactly how the underlying algorithm works. The only variable that must remain secret is the key. This sets up a paradox in cryptanalysis. Novices often assume that generating an impossibly large key space automatically equals computational security, but scale alone cannot protect a flawed architecture. Consider the historical substitution cipher. Its mechanism is simple. It replaces every letter in the plaintext with a different fixed letter from a scrambled alphabet. Because the English alphabet has 26 letters, the total number of possible scrambled alphabets is 26 factorial. That generates roughly 2 to the power of 88 unique key combinations. Blindly guessing and checking 2 to the 88th power of keys, an exhaustive brute force attack, is completely infeasible, even distributing the workload across thousands of modern processors. Yet, the substitution cipher is trivial to break. Its resistance to brute force guessing is irrelevant, because the algorithm preserves the underlying statistical properties of the original text. This raw ciphertext block illustrates the problem. Without the key, it appears to be a completely random sequence of characters. But this bar chart shows the standard letter frequencies of the English language. Human language is not uniform. The letter E makes up almost 13% of typical text, followed closely by T at about 9%. Because the substitution algorithm is fixed, the ciphertext inherits this exact distribution. We simply count the characters in the encrypted block and map the known distribution directly onto the results. If the letter Q appears 13% of the time in the ciphertext, Q is almost certainly E. We do not have to guess. The statistical constraints immediately lock the most common letters into place. By identifying just 2 or 3 high-frequency letters, we solve for the most common words. Once those pillars fall, that massive key space of 2 to the 88th power undergoes a total mathematical collapse. Computational security is a product of structural engineering. Algorithms must mathematically decouple the ciphertext from the underlying patterns of both the key and the plaintext data. The mathematician Claude Shannon laid out the formal axioms for doing exactly that. He identified 2 primitive operations required to build strong digital encryption. The first is confusion. This relies on nonlinear substitution to completely obscure the mathematical relationship between the encryption key and the resulting ciphertext. The second is diffusion. This uses exact bit permutations to ensure that changing a single bit in the plaintext spreads out, flipping multiple bits across the final ciphertext. This truth table shows modulo 2 addition, commonly known as XOR. It is a highly efficient binary operation where matching bits output a 0 and differing bits output a 1. Crucially, applying the exact same XOR operation twice perfectly inverts the process, recovering the original data. We can apply XOR in a continuous flow to create a stream cipher. The plaintext is encrypted bit by bit against a continuous sequence of noise generated by a cryptographically secure pseudo-random number generator. Stream ciphers are fast, but for securing complex data systems, architects often turn to block ciphers. Instead of a continuous stream, a block cipher applies Shannon's concepts iteratively to fixed, discrete chunks of data. This flowchart illustrates DES, IBM's blueprint for modern block ciphers. A 64-bit plaintext block, X, passes through an initial permutation, then drops through 16 identical rounds. Each round uses distinct subkeys, derived from a single 56-bit master key. This macroscopic looping structure forces the data to continuously fold over itself. By the 5th round, changing a single bit of plaintext alters an average of half the output bits, a property known as the Avalanche Effect. To see exactly how that diffusion is achieved, we look inside a single round at the Feistel Network. The 64-bit block splits symmetrically down the middle, creating a 32-bit left half, L15, and a 32-bit right half, R15. Simultaneously, the algorithm prepares the round subkey. It passes the initial key block through this permuted choice grid, known as PC1, to strip away the parity bits. The right half of the data enters the central function, where it is expanded and mathematically mangled by the 48-bit subkey to generate nonlinear confusion. That confused output is then carried over and XORed directly against the unaltered left half. Before dropping into the next round, the architecture executes a structural swap, physically crossing the left and right pathways, so the data enters the next stage inverted. After the 16th round, the halves undergo one final swap. The complete 64-bit block is pushed through a final permutation to become the finished ciphertext Y. The engineering elegance of the Feistel swap is that it makes encryption and decryption functionally identical at the hardware level. To decrypt the ciphertext, you simply pass it back through the exact same physical circuits, feeding the subkeys in reverse order. There is a strict boundary between the structural integrity of a cipher's math and the limitations of its parameter sizing. Architecturally, the Feistel network was remarkably robust. It resisted advanced differential and linear cryptanalysis for decades after its release. Its fatal flaw was entirely parameter-based. A 56-bit key generates too few combinations to withstand the scaling of modern hardware. By 1998, the Electronic Frontier Foundation utilized custom application-specific integrated circuits to build the deep crack machine. It systematically checked every possible key and dismantled DES in under 56 hours. Mathematical invulnerability to analysis is useless if the total quantity of key combinations is smaller than the adversary's raw computational throughput. When securing continuous datasets like computer files or network traffic, using a single block cipher, we use what are known as modes of operation. The most naive approach is Electronic Codebook mode, where every 64-bit chunk of data is encrypted entirely independently of the others. This animation shows the critical vulnerability of that approach. Because the cipher operates statically, identical plaintext blocks always produce identical ciphertext outputs. The encryption holds, but the overall file leaks clear structural metadata. To seal off this metadata leakage, engineers developed Cipher Block Chaining, or CBC mode. Here, the output of the first encrypted block routes backward into an XOR gate, mathematically mixing with the next plaintext block before it even enters the cipher. This sequential feedback loop guarantees that even if a file contains thousands of identical plaintext blocks, each one will produce a wildly distinct ciphertext. Modern cryptography relies on this exact synthesis. You must deploy an unbreakable algorithmic core to protect the bits, and a robust chaining architecture to guarantee diffusion and integrity across the entire system.